এগ্রিকালচারের একটা মেয়ে আছে, ও হয়তো ওখানে যাবে। Today we will discuss hypothesis testing. So, what is hypothesis? Do you have any idea about hypothesis? If I ask you what is hypothesis, hypothesis is a statement. Hypothesis is a statement that is yet to be proven. Yet to be proven. Hypothesis is a statement that is yet to be proven. Usually, in statistics, we frame hypothesis concerning the population parameter. Hypothesis for population parameter. So, if you read the history of science, you will find out that n number of hypotheses, a huge number of hypotheses has been framed by the scientist and proven by experiment or by some other means. So, our hypothesis is limited to the statistical hypothesis testing, and before going into detail of this, let us see the content of today's lecture. We will discuss the hypothesis testing for single population mean, for single population variance, for equality of two population means and equality of two population variances. So, come back to this hypothesis testing, and we have discussed the hypothesis statement that is yet to be proven, and there are we will consider two type of hypothesis. One is H0, which is known as null hypothesis, and another one is H1 or HA, which is known as alternate hypothesis. Null hypothesis is an assertion about a population parameter, and we believe on it unless it is proven statistically otherwise. And alternative hypothesis is the negation of H0. Alternate hypothesis is negation of H0. Okay. Let us see one example here. The manufacturer of a mobile handset claims that the mean recharge period for the battery of its newly launched mobile set is 7 days, beyond which it has to be recharged. As a busy person traveling frequently, Mr. R found it interesting, but he wanted to assure whether the claim is true or false. So, here our null hypothesis is the mean recharge period is 7 days, which is the population mean. We are basically talking about like this, that null hypothesis mu equal to mu 0. In this case, mu 0 is 7, and alternative hypothesis is that mu not equal to mu 0. That means not equal to 7. And if this is the case, as we told that we will believe on null hypothesis so long we are not able to prove that it is wrong. So, you have to prove it statistically. So, what is then the what are the steps? The steps are identify first your null hypothesis and alternative hypothesis. Then you definitely find out the appropriate sampling statistic, then obtain sampling distribution theta if the statistic is theta when the null hypothesis is true. Please keep in mind, this is very important concept, that when null hypothesis is true, that time you are finding the distribution of theta, that is the sample statistic. What you do? You collect sample, let size n, and you compute the parameter from the sample. And what we are trying to say here, I told that this is what is basically the statistic is theta. Instead of cap, we have given only theta. For example, this theta will be x bar or theta cap, that is x bar, which is basically estimate of mu. Now, this x bar is a random variable, and what you require to know, you require to frame an appropriate statistics. If it is x bar, fine. If it is not x bar, something else, that statistics you find out. For example, when we talk about x bar, we usually frame z, that is x bar minus expected value of x bar by sigma by root n, that we usually frame. Here our null hypothesis is H0 mu equal to mu 0. We all know that expected value of x bar is mu. So, then we write sigma by root n. Now, we have assumed that H0, from H0 we have seen that mu equal to mu 0. So, that means you can write this one mu 0 by sigma by root n, and this is my statistic for which you require to know the distribution. What I said here, that is obtain sampling distribution of theta when H0 is true. So, that means the sampling distribution of the here your x bar, which is nothing but we are converting it into z, and we are writing mu 0 instead of mu, as we are hoping that our null hypothesis is true. And then what you will do, you find out the critical value. What do you mean by critical value? In this case, if it is a z distributed, my distribution will be like this. This is z. Then we want to see that basically this one is z equal to 0. Now, this quantity x bar minus mu 0 by sigma by root n, this quantity follows z distribution, all possible values, all values here, these are possible. If it is sufficiently away from that z, that mean value, z mean value, then we will conclude that mu is not equal to mu 0. So, that is why we will frame critical value in this side, either this may be your, this is your alpha by 2, and or this side sufficiently away, this side, this is your alpha by 2. What we mean to say, if the computed statistics, which one is this one, in this case, if this value falls in the right hand rejection region or left hand rejection region, then we conclude that H0 is rejected, not true. That means H1 is can be accepted, that is mu not equal to mu 0. Then computational, what you will do first, you collect data, that what you have done. In this particular case, what way you will proceed? You will proceed like this, you collect data for x, which will be x1, x2 like xn, then you will compute x bar, which is 1 by n I equal to 1 to n x I. Then you will compute the statistic, which we are talking about z, that x bar minus mu 0 by sigma by root n. Now, please remember that sigma will be given. If sigma is not given, then sigma cap will be S, and in that case if n is sufficiently large, then you will be using Z distribution like this x bar minus mu 0 by sigma by root n. So, this is the computed Z basically from the data Z computed. Now, you have to choose alpha. So, your next step is choose alpha. You have seen that what is the error you are going to consume. If you say alpha is 0.05, this is also known as probability level of significance. If you say alpha equal to 0.05, then your point will be like this, your rejection region will be like this. So, suppose this one is alpha by 2 and this side this is also alpha by 2, then this is your rejection region. This side this one is rejection region, and in between this is the acceptance region. Okay. So, you have your distribution and you know the that level of error you are trying we will consume, and then what happen, based on this you will find out an interval which is acceptance interval, and beyond it is, as it is a two-tailed case. So, either right hand or left hand, when it goes beyond the critical value, that is z alpha by 2 right hand side and minus z alpha by 2 left hand side, when it goes beyond this you will reject the null hypothesis. So, what you do then? You have already computed z, from table you are getting the z alpha by 2, either it is the mod value you have to take. If z computed is greater than mod of z alpha by 2 absolute value, then what will happen, that either you will come into this side or this side, other way this may be negative also. Okay. So, you do one thing, you just change a little bit, that mod of this also will come under this side. I will take mod in both sides. So, if this one is my 0 value, now if z value is here, this will be positive and this side will be negative, and you will be seeing the alpha value from the z alpha value by 2 value from the table. Usually this one will be a positive value. So, you may not take mod here, no problem. So, the absolute value, if it is more than z alpha by 2, okay, more than or equal you can write. So, that means that what we are saying here, we are saying that if it falls here or it falls here, then it is sufficiently away from the mean value. So, H 0 mu equal to mu 0, that can be rejected. If I reject H 0, that means I am accepting H 1. Okay. Alternatively, I can say that I accept H 0, H 1, not H 0, you are rejecting H 0. So, actually either you will be able to reject H 0 or you will be, suppose your Z value comes here, that is within this acceptance zone, then you will say fail to reject H 0, fail to reject H 0. Okay. So, this is the procedure. The procedure says, first you must know that what is the problem, and then the appropriate variable you will find out from the population point of view. You collect a sample, from that sample appropriate statistics you generate, then you create the null hypothesis and alternative hypothesis for the population parameter of interest, and then using the statistic as well as its distribution, then you compare the computed value of the statistic and as well as the critical value from the sampling distribution of that statistic. When you compare, if you find out that the computed value is more than the absolute value of that computed statistics is more than the tabulated value, then you will reject null hypothesis. Otherwise, you say fail to reject null hypothesis. Okay. You see this figure, and I know that last class you have also seen the same thing. What we are talking about here, if it is population from normal or non-normal, whether sigma known or sigma unknown, and the condition of the sample, that means the size of the sample, whether it is large or small, and depending on this, all of we have seen under interval estimation that your quantity, that statistics may follow Z distribution, may follow T distribution, or you may not get any parametric distribution. So, this one x bar minus mu by sigma by root n, that is for the first case, like second case also same. Third case, your sigma is replaced by S, fourth case also sigma is replaced by S, but sample size small, that is why it is T distribution. Okay. So, if you use T distribution, what is the same thing? You will calculate the statistic, that is T computed will be your x bar minus mu 0 by S by root n, and then you will be finding out T tabulated. That T tabulated means basically you require to know the degree of freedom n minus 1 and alpha by 2, because T distribution is also a two-tailed distribution and your hypothesis also two-tailed hypothesis. The way you have created hypothesis, you have created hypothesis like this: H0 mu equal to mu 0 and H1 mu not equal to mu 0. That means both side is open for you. So, if it goes this side or this side beyond this level, you are not accepting null hypothesis, rejecting the null hypothesis. Okay. So, this is your T distribution and the mean value will be definitely 0. Okay. Here is one important point: when you go for two-tailed distribution, when you go for one-tailed distribution.
So, for mean it should be two-tailed. For variance so chi-square, that should be chi-square is 1, means only positive values are there.
But is it true that for all the time that for mean you will go for two-tailed, or there is something different? Okay. Suppose here in this example we say that recharge period of a battery, that is our example, recharge period. As a user, what you want? You want the more the recharge period, it is always better. Now, for recharge period, if you test like this, that H0 mu equal to mu 0 and H1 mu not equal to mu 0, suppose your that computed value falls here, Z value or T value, suppose T computed is here. So, now this is the smallest to largest. So, but the manufacturer is claiming that it is here mean value, it is the manufacturer claim. He is saying that this is the mean value. Now, you are testing that whether manufacturer claim is right or wrong. Now, you have collected data and you found that your that T computed or Z computed depending on the distribution, it is, in this case we are talking about T distribution, it is falling here. So, null hypothesis is rejected, fine, that means alternative hypothesis is accepted. So, in this case, do you go for the handset? You will not go. because the mean value is much lower than claimed. What will be in your favor? In your favor, if the value lies in other way, that means if the computed value comes here, that is your favorable case. You are rejecting, so long it is in between this, it is nothing but what is the manufacturer claim is there, that is case. If it comes here, this side, it is more than that. So, what you may be interested to create null hypothesis like this, mu greater than mu 0. You may not be interested to test this mu not equal to mu 0, you may be interested to test mu greater than mu 0, means the manufacturer is claiming it is 7 days, fine, 7 days is good, you may be happy, but you are thinking that if it is more than 7 days, that is better. So, in this case, see, it is mu only, but if I go by this two-tailed distribution, your hypothesis for alternate hypothesis, and you cannot by the, you may reject H 0, but it may not go in your favor. So, as a result, what it is said, that it is always better if you do like this. First you understand what is the variable. If suppose x is your random variable, what type of variable it is? Is it lower the better type, or is it higher the better, or it is nominal is the best? Getting me? For example, suppose the sulfur content in steel, percentage sulfur in steel, we do not want that sulfur content, more sulfur content, in fact 0 sulfur. So, it is lower the better. In this case, what you want? Suppose this is the sulfur content. So, ultimately you will be looking for the lower side. So, that means you will create a value that is the maximum value what you want. Your acceptance region, your zone of working will be region will be this. You do not want higher one. Now, if you plot, what will happen? You may find out distribution like this, let it be like this. So, you will go for the left hand side. For the higher case, it will be just reverse. You will fix a value here, somewhere here, and you want this side. Now, you can fix here or somewhere here, but ultimately you see lower the better and higher the better case, means one tailed this test is better. Only when nominal is the best, means there is a target, and if you deviate from the target, if you deviate from this target this side or this side, this is not desirable, then your two-tailed hypothesis is better. So, for both the cases, this is one-tailed, and for this two-tailed. Getting me? When you frame the hypothesis, null hypothesis, there is absolutely no problem, because from what you are doing, you are basically telling some value for that hypothesis. A statement you are making, it is something like this. Usually we say it is equal to this in statistics, hypothetical testing. But what will be your alternate hypothesis? Now, if you use one-tailed hypothesis, what will happen then with for the critical value? Okay. In two-tailed case, you have taken here, suppose this two-tailed case, if I say this is my left side, this is right side, you have taken z alpha by 2, or you have taken t n minus 1 alpha by 2, this side or this side, or here minus z alpha by 2 t minus t n minus 1 alpha by 2. But when it is one-tailed, suppose so long it is within this, you are accepting H 0, when it is going this side, you are rejecting H0, then it is one tailed. In that case, this will be Z alpha if Z distribution is applicable, or it will be T n minus 1 alpha. In the other side also, if you think that no, this this one is this left tail only, this also alpha, getting me. So, then this is minus n minus 1 alpha, and here it is, this value is alpha. Now, there is a relationship between this hypothesis and confidence interval. See, if this is alpha, then this side is 100 into 1 minus alpha, that percent, and similarly here what is happening, this is 100 into 1 minus alpha, the interval, that is why alpha by 2 you are making. Okay. So, this is what our hypothesis testing for single population mean. This is one example. Last class we have described. We said that MSD is a problem with industrial workers, particularly the crane operators in heavy industry. Now, a random sample of 76 responses yielded a mean of 7 and standard deviation of 4. Population standard deviation is also given. Conduct hypothesis testing for alpha equal to 0.05. That means, what you require to say that you are basically mu equal to 7, that will be your null hypothesis, and what will be your alternate hypothesis? Your null hypothesis is mu equal to 7 here. Okay, let us see the alternate hypothesis, mu not equal to 7. Okay. Now, here the thing is that as a manufacturer, as a management point of view, you want to see that no, it is not 7, it is below 7. From operator's point of view, they may say no, not it is not only 7, it is more than 7. The operator who are using the crane, they will be saying that we are suffering more. That the management who are basically maintaining the system, they will be saying no, it is less than 4, less than 7. So, then from which side you are testing the hypothesis, that is also important. Who is who is the owner of this hypothesis in that sense. Okay. And I have given here that what will happen if population standard deviation is not known. You know 7 deceived responses, even if population standard deviation is not known, but sample standard deviation is known, Z distribution will still be applied. What will happen if population standard deviation is not known and n less than 30, T distribution will be, you will be getting the critical value for comparison from T distribution. Are you getting similarity with in confidence interval? There you have created the same way, you created this first you found out the statistic, then in that case what happened in when you have found out some statistics like x bar minus mu by s by root n, then you have created like this minus T alpha by 2 n minus 1 T alpha by 2 here n minus 1, that you have created, and as mu was not known to you, last class you have seen, you do not know mu, you created a range for mu. What happened here in this hypothesis testing case, mu is given as mu 0, which is under H0, and we are saying this particular quantity follows T distribution when H0 is true. That is why I told you in the beginning that you please keep in mind that whatever statistics you will generate and the statistical sampling distribution you will consider, that is true when H0 is true. Then now instead of mu you write mu 0, so that means this value you know, entire value you know, and you also know the critical values. This is left side critical values, right side critical values, both values you know. whether this value is less than this value or this value is more than this value, that you are finding out, and accordingly you are rejecting null hypothesis. And I know how to use Z table, that is very much known to you, T table also. Now, when you make hypothesis testing, you basically take certain decisions. Okay. Hypothesis testing is a basically decision making. In confidence interval estimation, that time you are not making any decision. Here in hypothesis testing, you are making a decision based on the sample data. Now, there is possibility that there are 4 scenarios. First scenario is, you just think like this, that you have considered hypothesis H0 as something, some statement you made in favor of H0. That statement may be true, may be false. Now, if statement is true, that means the hypothesis, null hypothesis is true, then depending on that, based on your analysis of the data, you may accept it, you may reject it. If your null hypothesis is true and you have accepted it, that is the right decision. Again, if null hypothesis is false and you have rejected it based on your data analysis, that is also right decision. Problem comes when H0 is true, but you have rejected it, or H0 is false, you have accepted it. When H0 is true, you have accepted it, that is known as type 1 error or alpha error. Okay. And when your H0 is false and you have accepted it, it is type 2 error or beta error. What is the physical interpretation of this? How do you get the physical meaning of decision making? If you see that manufacturer risk versus consumer risk, getting me? There is a production process, producing something you are producing, and there is suppose some testing like this, and it will be good or it will be bad depending on the test here. Let it be. If it is good, it is going to the customer. Bad, it is going back, means it is rework or scrap or something like this. This is of my production process. So, what you do basically here, you do certain sampling here. In quality terminology, it is acceptance sampling. Acceptance sampling. Suppose you are doing this one this is manufacturer, you are the customer, or other way also. Suppose you are purchasing raw materials, there is supplier supplying raw materials, and here is a quality control acceptance sampling. Again, if it is good product going to you, good, but if it is bad, it is again coming back to supplier. All these two places, it is an acceptance sampling case. In the first case here, manufacturer is producing something and there is a sampling, acceptance sampling scheme for the customer. Based on the data, he may accept or reject. That means good or bad is coming based on the data. In this case also, supplier is sending something, manufacturer is testing it, and according to the test, either returning to the supplier or accepting it. Now, in this case, what will happen? Suppose the manufacturer produces the right one, but test says it is wrong one. So, your error is type 1 error, because manufacturer produces the right one, manufacturer produces the right one and you have not accepted it, type 1 error or alpha error, fine, this is good because the produced item has gone back to the manufacturer. Now, suppose what will happen if manufacturer produce the bad one and your scheme accept it, then you will get a bad product. The second one is more problematic because the bad product goes to the market. It is problematic for the customer, more problematic for the manufacturer also. Because next time what will happen if someone else want to purchase this, as a customer you will say, "I don't purchase, it has lot many problems." So, as a result what happened here, actually customer do not do this acceptance sampling at the market level, that, but the manufacturer himself do certain sampling here once the production is completed, how many to be sent to the market based on certain test. Getting me? So, hypothesis testing is nothing but a decision making, and many times these decisions are very, very crucial decisions, and you must know what is the alpha error and what is the beta error. Another issue you go through if you find time, that is operating characteristic curve. Popularly known as OC curve. Okay. We say that type 2 error is beta error and 1 minus beta is the power of the test. Beta is the power of the test ratio. This operating characteristics curve can be understood. Suppose you see, I am giving one example here. That example is that you think of a quality characteristic and that characteristic suppose follows this normal distribution. This is my quality characteristic, let it be some variable x. Now, its mean value will be here, but over this is nothing but a process which is producing something, some output which is measured through x. What happened, this over time because of maybe wear and tear or because of your what I can say that not perfect maintenance, this ultimately the process mean, that means the x value, the mean of x, it will basically shift. Suppose initially this was my mean value, but because of wear and tear and imperfect maintenance, this mean value may shift in this direction or in this direction, depending on the quality that what is happening in the process parameters level. So, in that case, suppose I want to check if there is, but it is very difficult to change that this mean shift has taken place. Immediately you will not find out the change. When the change has taken substantially, then only, suppose this mean has gone to this level, this is the new one, new mean, then you find out that much change has taken place. So, that type of, if I write in this side, that is mean change or mean drift, okay, and this side suppose the beta error, beta value, what will happen, you get in certain curve. When the beta is what, type 2 error, there is change, but you are not able to detect. So, so long the change is small, you are not able to detect, that means you will accept. So, your things may be like this, it may be like this. It all depends on this type of curve will come under operating characteristic. This is very important, because when you are able to find out the change has taken place, that is very, very critical for even not only manufacturing or other system also, it is very, very critical. Now, we we will go for the population variance, and I am sure that you will appreciate one thing here, that you know how to go about hypothesis testing for population variance also. What you require to know? You require to know the statistic. What will be the statistics in case of population variance? We say that chi square is n minus 1 s square by sigma square. What is your null hypothesis? Sigma is sigma 0. What is your alternative hypothesis? Sigma not equal to sigma 0. Okay. So, then your computed value will be chi square computed, which is n minus 1 s square by sigma 0 square. So, as you have taken two tilt condition here also. So, what you will do? You will just find out here it is chi square alpha by 2, and here also chi square 1 minus alpha by 2, and all of you know that chi square distribution, and one parameter of chi square distribution is the degree of freedom. So, here you require to write down degree of freedom n minus 1, here also it is n minus 1. Then if you find out that if your this value will fall here or here, you will reject null hypothesis. So, that means you have to compute and find out where it is falling. Okay. And as you know that variance is also a such a what I can say parameter, we do not want more variance, basically we want less variance always. In that sense, if you are interested, then maybe you can go for one tilt also. But here what is the issue is that one null hypothesis is given, you are trying to prove that null hypothesis true or false. So, in that case, alternative hypothesis if you create like this, absolutely there is no problem. But I have given you some example. Based on that example, if you go, that means from the problem to hypothesis, then I think lower the better, higher the better, nominal is the best, that particular concept you must use. And again, if I go for the next one, that one also easy for you. This is one example I have given, and nothing, no problem at all. What is the our next topic? Next topic is you want to test whether two population means are equal or not. Equality of two population means. What you will do here? What is the random variable here? x1 bar minus x2 bar. So, this x1 bar minus x2 bar, that will follow normal or z, that is t distribution depending on the conditions. And all of you have seen that x1 bar minus x2 bar minus expected value of x1 bar minus x2 bar divided by that variance of x1 bar minus x2 bar, this follows z. We are assuming that sigma and other things are known, you know z or t, that is that, again no need of discussion further. So, 0 1. Then what will be your here that z computed? If I use z value, then z computed is x1 bar minus x2 bar minus this is mu 1 minus mu 2 by this one we have seen last class n1 plus sigma 2 square by n2, that we have seen. What is your null hypothesis here? H0 mu 1 equal to mu 2. So, that means this quantity becomes 0. So, your z computed becomes x1 bar minus x2 bar by square root of sigma 1 square by n1 sigma 2 square by n2. You know n1, n2 and sigma 1, sigma 2, compute this and then again find out your set your alternate hypothesis mu 1 not equal to mu 2, that is two tailed case. So, z alpha by 2 minus z alpha by 2, find out where it is falling. Is it falling in this region or it is in between these two? This is acceptance, this is rejection, this is rejection. For whom? For null hypothesis, correct? Question here, anything clear? Basically, the crux of the matter is knowing the appropriate statistics and its distribution. Why that is required? Because then only you will be using the table, otherwise you cannot frame anything. It will be not a parametric one, it will be different kind. For parametric case, it is the must. You must know the statistic, appropriate statistics and its distribution, then things are very simple.
Sir, why we call it null hypothesis? Because our target is proved by contradiction. Is it we always like to negate it?
Actually, this is the what I can say, this way it is developed. You want to negate it, definitely you want to negate it. Null hypothesis, the word null, I have no idea about the word null, why they are writing null, but I can say that as you are saying that alternative hypothesis, the purpose of alternative hypothesis is that you want to reject the null hypothesis. Okay. You will claim in such a manner that you will do in such a manner that it is possible to test null hypothesis. As such, why the word null is coming? Difficult for me. Okay, so I may see this one later on. Otherwise, this is the general way. This is a very good question. Basically, I think yes. Why the word null is used? I can give you one explanation. Sometimes what happened, I have seen in structural equation modeling, they have taken covariance matrix and then only the variance component they consider and other component they put it to 0. So, I am not 100% sure that null is basically the void or 0, getting me. So, if this is the case, then when we test, you will find out, you create, suppose you are making z test, then that z test, that z value is 0. If z value is 0, so long your statistics is close to 0, you are accepting this. When you are rejecting, you are saying if that my computed value is sufficiently away from 0, getting me. So, from that analogy I can tell you, because of this 0, you are getting me, because of this 0, because what I am doing basically, I am computing the z value, that statistics value. I know this will follow certain z distribution, where the mean value is 0, because you are testing for mean. So, it is sufficiently away from 0. So long it is close to 0, that means so long within this region, so it is in the null region. If I say null equal to 0, null means void, void means 0, that sense. I think this may be but one of the explanation, but I am not 100% sure that whether this, I think this can be thought of. This is the example, as I told you in last class, that the method of teaching is tested and two population standard deviations are given for section 1, that method A it is 5 and method B it is 10. in your confidence interval you have taken these values, but in when you have used S pooled, that time what happened, that time you have assumed that these two values are not different. We were here we are interested to test whether these two values are really different or not, and that is the difference between two teaching methods. No, here we are basically doing the difference between 80 and 70, that is mean difference we are doing, and considering population at 5 and 10. Okay, not that what I said that chi-square distribution here. Now, you come to the special case. Okay. What is the special case? Sigma 1 equal to sigma 2 equal to sigma. This time you will use SP square, that is pooled variance, rest of the things remain same. And your statistic, that basically computed value will be under H0 mu 1 equal to mu 2. So, if I use t, computed t will be x 1 bar minus x 2 bar minus 0, because mu 1 minus mu 2 equal to 0, divided by SP square root of 1 by n 1 plus 1 by n 2, and go for tabulated t n 1 plus n 2 minus 2 alpha by 2. If my computed t is more than or less than, depending on which side it is, that the tabulated t, you will reject the null hypothesis.
One, though it was from last class. This is just a special case of the
Original one.
Original one. So original one was the
Sigma 1 square by n 1 plus sigma 2 square by n 2.
So, in general, we know that special case should hold the original one also, is in other cases.
Okay.
So what is the requirement of the formulation of the separate type of formula?
Correct. No, because under this special case scenario, what happened, actually all these whatever the distribution you are finding out, these distributions are governed by the number of parameters as well as the size of the sample, all those things are involved there. Now, what happened, when the special condition arise that sigma 1 equal to sigma 2 sigma, then if we convert this we find out SP square, and accordingly we will go, that power of the test is much better. You are getting me? Always there is a possibility of error, because alpha error is or beta error is there, confidence interval, the power of the test will be better. That is why these special cases are found out, and they are also reported, and most of the times we use this. That is why what he said, if you find out that the two population variances are equal, that you first find out, then you go for the special case, do not use the general case. General case is many a times general case, because general case will give you some result, but if this special case will occur in
This is better.
Always better. This is another example that we want to equality of performance between two medicines, confidence interval case you have seen. Now, equality of two population variances. Should I go for this? I think you all will be able to find out this. When you say that equality of two population variances, you must know the distribution of the ratio of two population variances. Last class we have proven it that it will be basically F distribution. So, your F n 1 minus 1 and n 2 minus 1, and definitely you will be creating certain alpha values. Okay. and that will be your tabulated one. And what was the statistics that time? Statistics we considered f equal to S1 square by sigma 1 square by S2 square by sigma 2 square. What is our hypothesis here? H0, that sigma 1 square equal to sigma 2 square. So, sigma 1 by sigma 2 whole square is basically this is 1. So, your f is resultant f basically coming S1 square by S2 square. So, you want to test with the tabulated value, and if you find that tabulated value is less than the computed value, reject the null hypothesis. Here some special cases also occur, basically depending on the sigma 1, sigma 2, that which one is more, which one is less. You go by this Freud and Miller book, Freud and Miller basic statistics, that book, engineering, I think this is basically introduction to statistics. That book you go through, you will be finding out many more cases are there. This is F table, and I told you last class that when the confidence interval as well as this hypothesis testing, these are the some pioneers. Hypothesis was ANOVA, in case of ANOVA, that Fisher has tested so many hypotheses in his many experiments what he have conducted. And for hypothesis testing, this book is good book. This is Excel AD complete statistics. I have seen this book is a very good book. You can go through book, it is a compact one. In addition, as I told you that Freud and Miller, that statistics books also you go through, you will find out that fantastic. So many good books are there, and particularly for basic statistics is concerned, univariate statistics is concerned. Multivariate statistics books, yes, good books are there, Johnson, Richard and Hare et al. And some more books are there, but compared to univariate case, multivariate books are very limited. So, next class what we will do, we will basically talk about multivariate descriptive statistics. Okay. So, this is the end of today, this is the end of our basic or prerequisites. Please remember what I have told you under this basic statistic is very minuscule. I have told you very simple, just for to get some idea that what is happening, what will be is there. But in general, one univariate, that basic statistics book itself is 1000 pages. Getting me? So, if you really want to get your fundamentals very strong, you have to have some good books on basic statistics also, and you have to go through. And I have given you some of the things what the concept, this concept we will be using in multivariate that lectures also, so that you can easily grasp. Means I will first tell you, okay, in univariate you got this one, see how we are converting the same concept to multivariate. So, those many portions also only I have taken into consideration. It is not the totality of univariate basic statistics. Okay. Okay then, thank you.